This next lesson is called Simplifying Algebraic Expressions Involving Exponents. This lesson is a shorter lesson because really it's a culmination of the first two lessons, learning to work with rational exponents and then learning to work with radicals. So now what we're doing is combining the two, and we're basically simplifying algebraic expressions, and they will have either exponential components to them or radicals. So we'll be dealing with roots and dealing with powers of various kinds, with integer exponents and with rational exponents, and simply going through steps to simplify them. In the mind's eye, the first task that I'd like you to do is simply take this rational expression and make all the exponents positive. To do that, remember that we simply have to move the powers from the numerator to the denominator and vice versa, and then change the sign of the exponent. So starting with the top, I want this a to the minus 3 to have a positive exponent, so I will move it to the numerator. And similarly with the b to the minus 8. The x to the minus 2 in the numerator on this original expression, I will now move to the denominator, and I will have x to the 2, and the y to the negative 5 will now be y to the 5. Here I have the steps for simplifying exponential expressions. So what we want to do is simply give an example here for each of these descriptions so that it's clear that we know what they mean. Now ideally, once again, what I would have you do is pause the video and go ahead and come up with your own examples for each of these. That gives you a chance to really think about what they mean, and then check back to see if your examples suit the situation. So the first step is to express all radicals as powers. So I'm going to put a radical in here. Let's say the cube root of x to the 4. If I want to express that radical as a power, remember the rule, what we do with the root and what we do with the exponent in terms of the fractional exponent of the power. So this would be x to the exponent goes in the numerator. So we would have a 4 in the numerator, and the root goes in the denominator. The next example would be simplifying exponent rules. An example would be to have a couple of variables with exponents that we can cancel. And again, you're just making up examples here. So in this case, I would simplify the numerator first. So 2/3 and 1/3. You can see I made it easy for myself. That's 1. And then I have the x to the 5th and the y to the minus 2. And one thing is that I would now make that y positive and move it to the numerator. Just so you know, the other way you could look at it is imagine that there's a y to the 0 here, because remember we reviewed in an earlier lesson that anything to the 0 is 1. So you could put a y to the 0 here and then do 0 minus minus 2. And again, you would get plus 2 in the numerator. We have y to the 2. And in my head, I was thinking ahead here, right? I've talked about planning ahead. I see that this 5 is greater than the 1. That's the exponent on this x. So I'll be leaving the x power in the bottom or in the denominator. So 5 minus 1 is x to the 4. And that would be an example of simplifying using exponent rules. And this is similar to what we did in the minds on, rearranging powers between numerators and denominators to achieve positive exponents. So I can make up an example where I have some negative exponents here. And I'll do the same in the bottom. They wouldn't have to all be negative to illustrate the point, but I might as well do that. And so first thing I'm going to do is, because there's no powers of the same base in the numerator and the denominator, I would make all of them positive first. You could go ahead, of course, and do your simplification, but here we're illustrating rearranging the powers to get negative exponents. So rather than simply doing the simplifying that we probably would do when we're working on this, we're going to illustrate the idea of making them all positive first. So I'm going to take all of these powers in the numerator, denominator, and put them in the numerator and make their exponents positive. Z to the positive 2. And down here I would end up with an x to the positive 1, but I don't need to write the 1. Y to the exponent positive 5. And z to the 3. Now this didn't ask us to simplify in this case, but normally we would, so let's go ahead and simplify. So I'm planning ahead here, seeing where these are going to end up. This will end up with an x power in the numerator because this is larger than that exponent. The y will end up in the denominator and the z will end up in the denominator. So I will have an x term, x power in the numerator. So that's x to the 4 minus 1 is 3. And in the denominator, y to the 5 minus 3 is 2. And z to the 3 minus 2 is just z to the power 1, but I don't need to write the 1. And the last example asks for us to evaluate simplify numerical expressions. So it's giving us an example of that because in our algebraic exponential expressions or rational expressions that we will have, there will be numbers involved that we will have to simplify along with the variable examples. So I'll make up an example here that just has numbers. So 2 to the 3 times 3 to the 5 times 2 to the 6. I'll put another base of 2 there over 3 to the 4 times 5 squared. So I want to simplify this and evaluate it. And normally what we would do is talk about simplifying first, although if you're just working to get to a solution, it's certainly you're certainly welcome to do it either way. You could just evaluate this. There will be questions where you may be asked to write certain expressions as a single power to show that you are comfortable with the simplification using the exponent rules. So in this case, we're going to simplify what we can. So similar to what we do with the variable powers, 2 to the 3 times 2 to the 6, that's a total of 9 2's being multiplied, and 3 to the power of 5. And there's no simplification in the denominator, so 3 to the power of 4 and 5 squared. And now we're just going to simplify first. We can simplify these powers with a base of 3. So we'd end up with 2 to the 9, and then 3 to the exponent of 1, which is just 3, and a 5 squared. And so we see here that we will have, now I'm looking for canceling actually first, because it's convenient at this point in time, because we have multiples of a number being multiplied by itself, that we have factors that can easily be seen to be canceled if they are there. So there's no canceling here. So this question won't be reducing. In the denominator, we will have 25. Then we basically have 2 to the 9 times 3. 2 to the exponent 9 times 3. That's That's 1,536. There, now we have our 4 examples of these explanations or these steps that we've been given. Now, as I said, this is a shorter lesson because we've been practicing questions like this, simply not having them all combined in this way. So there are three examples here, one of them where you have to evaluate, and then you'll be able to go and practice this skill. So this first question is very similar to what we did in the first lesson, except that there's only one rational exponent here, and it's expressed as a decimal. Now, when you have decimals like this, you couldn't be faulted for coming up with an answer that has decimals because the question already started with decimals. But we could also convert that to a fraction and get an exact value. Since it has decimals, I'm going to leave it as a decimal and show you that that is a possibility. First thing we'll do is take these outer exponents and apply them to each of these factors inside the brackets. So what we have is 4 to the negative 2, x to the negative 5 times negative 2 is 10, y to the 6 times negative 2 is negative 12, all over 2 to the negative 10, x to the, now this negative 10 is actually going to take care of that 0.2, so we end up with negative 2, and y to the 30. Now what we need to do is simplify from numerator to denominator. I'm going to make the exponents on these numerical powers here positive. So I will write this as 2 to the 10. And then 10 is larger than negative 2, so we will have x to the 10 minus minus 2 is 10 plus 2. So that's x to the 12. And then in the y, the exponent 30 on the denominator is larger. So I'm going to put this 4 to the negative 2 in the denominator. That will be 4 to the positive 2. And then we have y to the 30 minus minus 12, which is 30 plus 12. That's 42. And all we have left now is to evaluate these. Now, I see that with this base of 2 and this base of 4, I can expect that there actually would be some canceling. Sometimes the canceling this way can be trickier. You're fine to do the canceling here as long as you're comfortable with it, or you can simply work out these values and then reduce them afterwards. So we need to know what 2 to the 10 is. 2 to the exponent 10 is equal to 1024. So we have 1024 x squared to the 12 all over 16 y to the 42. Now we can reduce this. It looks like 4 will go into both of those. Again, you can do that on your calculator. If we take 10 to the 24, which I already have on my calculator, and I put that using the fraction button over 16 and press equals, and I get that that actually goes in evenly. So it's no longer a fraction anymore. We get 64 x to the exponent 12 all over y to the exponent 42. And that's simplified. Now, in our steps above, it talked about changing the radicals to exponential form. In this case, we didn't need to do that, but now we have an example where we do need to change this to exponential form. And something to get used to is that when you have a root like this, like a fourth root over top of something, we can just think of all of this underneath of the root sign is having an understood 1 out here. And so when you have a fourth root like this or a fifth root, we can put a bracket and put the exponent quarter here. And we can take all of this. I'm looking ahead here, and I'm seeing that 4 times a quarter, because this would be a power raised to an exponent, and we're multiplying, that's going to be 1. So that will make it a lot easier for us than if we distributed this all the way through. You can do it that way if you wanted to right now, and it would still be fine. But I'm just doing some planning ahead here and thinking that's going to make it a lot easier for me if that times that is 1. So I'm going to leave this for the moment inside of the bracket. And then I'm going to apply that quarter first before I do anything else. So now you're going to see clearly what happens here. A quarter times 4 is 1. So all I have left is what was inside the bracket and no exponent on the outside to deal with. And looking at the denominator, minus 8 goes into 4, divided by 4 is minus 2. So now I have a simpler exponent to work with. And once again, just a reminder, just to work carefully through these. And if you go step by step, it's really not so hard. You just have to be very methodical and careful about it. Now I'm to the step where I start simplifying either in the numerator and denominator separately or between the two. And so I'm looking here, I don't see any simplification to do in either the numerator or the denominator. So I can start doing my division here and leaving values either in the numerator or denominator wherever they will be positive. And I have mixtures of fractions and decimals here, so I'm going to need to decide. And again, if you choose decimals and you make this 0.75, that's not wrong because this question already has a decimal inside of it. I'm going to choose to make this a fraction. 20 divided by 4 is 5. And then I see with the m's that 3/4 is bigger than minus 10, so that will end up being in the denominator. But 0.5 is larger than minus 2, so the n will end up being in the numerator. So my 0.5, or I said I was going to use a half, minus 2 is plus 2, so that's 2.5, or 2.5 is the same as 5 halves. In the denominator now, I just have the m, and that's 3/4 minus 10. So that's 3/4 plus 10. I'm going to write that over here just so you can think about the converting to a mixed fraction. So I have 10 3/4 converting from a mixed fraction to a improper fraction. I have 10 3/4. One way to do this is to take 4 and multiply it by 10, because 10 would be like 4 over 4 10 times, right? That's 10 ones. So that would be 4 over 4 10 times. So 10 fours is 40 over 4, right? 40 over 4 divided by 4 is 10. So what we can do is simply take 4 times 10 is 40 and then add the 3. So that's equal to 43 over 4 as an improper fraction. That leaves us with m to the 43 over 4. At this point, you might look at that and think it looks kind of messy with these fractions in here, that maybe you would think there should be something else to be able to do, but that there are questions that are going to end up like this. So that is as simplified as we can get it. Finally, the last example has to do with simplifying, and then in the end, taking values, specific values for the variables, and evaluating. At this point, I just want to point out that it is true that you could substitute these numbers in here and then evaluate this all numerically. But we also want to practice applying our skill of simplifying and then substituting those numbers in. A good practical application for this would be if we're in a situation in a workplace where um, we have a formula, it might be in a scientific field or engineering, and so we have a formula or a model that represents a situation that we're working with. And so we've created this model in order to represent it mathematically. And there may be many times that we're going to be substituting numbers in here and evaluating it because it's a formula that we're using over and over again. Or the other example may be that it's a formula that's going to be programmed into a computer. And so if we're going to do that, we want it represented as simply as possible. So we would simplify it first. So we're going to go ahead and simplify this first. And again, there's lots of decimals here. So 5 to the 0.1 and 0.25 to the on its own, we would be evaluating those numbers. But first, there's an exponent 10 here. So we're going to go through and simplify this first. This particular question has radicals in it, and again, it has decimals represented. A couple of things we want to do. We want to represent this radical as power. So we're going to make this quarter an exponent similar to what we did before. So the exponent will be 1/4. And then here we want to apply this 10 through that bracket. If we do that, we end up with 5 to the 0.1 times 10 is 1. Don't need to write the 1. X to the 4. 10 times 0.4 is 4. And y to the 2 times 10 is 20. In the denominator, we will write 0.25. And now we will write this expression here with an exponent of 1/4. Inside of this bracket, then we have 16x to the 20, and we have a y to the 6th. 5 divided by 1/4. Well, there's 4 quarters in one, so that's going to be 20. And we still want to simplify that denominator, so we'll leave the x to the 4. But the y to the 20, I can go ahead and simplify. The 20 is larger than the 6, so 20 minus 6 leaves us with y to the 14. I've already taken care of the 0.25 in the denominator, so what I have is 16 to the 1/4. Now you can write that out, or you can think in your head. I'll write it on the side here to help you think about it. 16 to the 1/4. It might be easier to think about if we think of it as a radical, or you can punch it in your calculator. That's the 4th root of 16, which is 2 times 2 times 2 times 2. So the 4th root of 16 is 2. So I have 2x to the 20 times 1/4 is 5, and then we have y to the 6th. Finally, 20 divided by 2 is 10. X to the 4 and x to the 5, the 4 is smaller, so that's going to end up being in the denominator. Y to the 14 over y to the 6. 14 minus 6 is 8. That's y to the 8 in the numerator. And then we have x to the 5 and the x to the 4 in the numerator. 5 subtract 4 is 1. So we have an x left in the denominator. So now this work actually becomes simpler, and you can see how if I was having to use this formula over and over again, or to program it in a computer, this is much easier to work with than this. And so this is one of the goals here, is to be able to take an expression like this and write it in a much simpler form so that we can work with it more easily. So now what we want to do is simply substitute those values. Now, what I prefer is, this was our simplification portion. I prefer that we come over and start new with that expression and show that now we're evaluating it. So we have 10 y to the 8 all over x. Y is 3, so that's 10 bracket 3 to the 8 all over x, which is minus 2. And now you can put that in your calculator. I see that 10 divided by minus 2 is minus 5. So what I have is minus 5 times 3 to the 8. Minus 5 times 3 to the exponent 8. And that's minus 32,805. And those are examples for simplifying these mixed exponential and radical expressions. And now you can go and practice that.